is on the circle. You'll have to catch up. This is review anyways. An angle whose vertex, and I'll even write this so it's legible. An angle whose vertex is on the circle itself. So to contrast, I could have, how about angle EFG is an inscribed angle because the vertex or F of this angle is on the circle itself. Angle EFG would be an inscribed angle. Central versus inscribed. Okay. And since we've already kind of talked about central angles quite a bit, we're going to focus today on inscribed angles and things we can gain from them. Specifically, the measure of an inscribed angle says the following. It says that the measure of an inscribed angle is half of the measure of its minor arc. An inscribed measure angle is exactly half as big as the measure of its minor arc. So for example, if I call this inscribed angle like angle 1, if its minor arc is, say, I don't know, what's a good arc measure for that? How about this is like, say, 70 degrees, then what's the measure of angle 1? Then the measure of angle 1 is half as big as its minor arc. So whatever its minor arc is, we'll divide it in 2, and we'll get the associated mark measure for our angle measure for our inscribed. I have a few diagrams, kind of extra pictures to go along with this. Can you read what those angle measures are? First circle, I have an inscribed angle, angle BAC. Its associated minor arc is 158 degrees. Actually, oh, I'm sorry. Well, it's not a huge deal, but I got to change something because this inscribed angle doesn't necessarily have to be a minor arc. Sorry. I'm going to change the word minor. Oops. I'm going to change the word minor to the word included. Say included, say between the two. I apologize for that. Included. It doesn't necessarily have to be minor, because you could have an angle that is very wide, and maybe it's more than maybe the arc is more than 180. There's nothing that says that could. I apologize for. I'm going to use the word included. Included as in the arc that's between the two rays of your head. So let's find the measure of angle BAC, find the measure of arc BC, let's find the measure of arc BC as well for each of those. try my new toy too. What's the measure of angle BAC?
79 degrees.
79 degrees, half of the included arc. Absolutely. Okay, victim number 2. Wow, Lane.
Oh!
How about that? Lane, what's the measure of arc BC?
I would say that's 152 degrees.
It's exactly 152 degrees, double of the included angle. If you know the included angle, we can double it and get the corresponding included arc. All right, and our final victim of round 1 is Hava. What's the measure of arc BC? 80.
Wait, do you like first class listening?
I did. Congratulations, contestants.
Yeah, well, extra.
No, you just nice job. Your book lists a second. Your book lists a second theorem / postulate. I didn't list it as a theorem or postulate because it's sort of common sense. It says that if two included angles intersect the same arc, what do you think is going to be true about the measures of those included angles? If two included angles intersect the same arc, what are we going to know about each of those two included angles? They better be the same measure. If, for example, angle EDF and angle ECF both intersect arc EF. That means each of these is exactly half as big as EF. And if they're each half of this, then they better be the same measure. So if I find two angles, two inscribed angles that intersect the same arc, or that have the same included arc, might be a better way to phrase that, then the angles must be congruent. They have to be the same measure. So let's find two pairs of congruent angles. I believe Abby already said that angle D and angle C are congruent. We got one pair of congruent angles. Can you find another pair of congruent angles in this picture? Okay. Angle E made from an angle F both intersect arc DC. So angle E are also congruent to each other. Let's, if you haven't already, let's find two pairs of congruent angles in our second drawing as well. All right, guys. Hopefully, we got these two pairs are drawn in from our diagram.
Now that I think about it, I did.
Guys, I'm gonna wait for you. These two pairs are the ones I got that are drawn in. Angle X and angle Y both have an inscribed arc of arc WZ. And in addition, angle W and angle Z both share arc XY. So those two angles must, in addition, be congruent. Okay. Your book has I can't remember if it's a postulate theorem in your book, but it's got something formal for it. I didn't put on the notes, but if you want, you can add it. We're going to shift gears slightly, and we're going to talk about things called an inscribed polygon. If something is inscribed, for example, our inscribed angle had its vertex that's on the edge of a circle. Okay? So if our inscribed angle has its one vertex on the edge of a circle, what do you think an inscribed, say, triangle? What's going to be special about an inscribed, say, triangle? What's going to be how is the word inscribed attached to our triangle going to affect kind of its shape? What's going to be true about our triangle if it's inscribed?
It's going to be on the triangle.
What is going to be on a circle? Okay, a whole triangle itself we can't put right on a circle because it's going to be that we'd have to curve the sides. There's going to be something about the triangle. It's going to be dealing with circles. Can be. We can have right triangles. That's true. Right triangles can be inscribed, but any triangle can be inscribed as well. What is this word inscribed going for? And recall an inscribed angle it's the only part of that angle that necessarily has to be on the triangle or on the circle is the vertex. So what do you think is going to be true about an inscribed, say, triangle? How many vertices? So if an angle has one vertex on, how many angles or how many vertices does a triangle have? 3. So how many vertices do you think are going to be on a circle if it's an inscribed? All 3. If it's an inscribed, say, quadrilateral, how many vertices are going to be on the edge of a circle? 4. So an inscribed polygon in general has it's a polygon whose vertices are all on the same circle. A polygon in general, just if it's inscribed, that means that all the vertices of a polygon lie on the same circle. We're going to look at two in particular, a triangle and a quadrilateral, in does of what that causes. Something special about an inscribed triangle is the following. If an inscribed triangle has a diameter for one side, then the following will be true. So we can have triangles in general can be inscribed, and that's cool. But a specific instance of an inscribed triangle is the following. What if we have a triangle that's inscribed, so the three vertices lie on a circle, and we'll do the following. We'll also make one of the sides a diameter. So what if we have this situation? What do we know about this triangle? What's going to have to be true about this triangle? Maybe I'll push you a little bit further. Do we know anything about any one of the angle measures of this triangle? What are we going to force at least one of the angles to be? And why? So not just like, I don't want to just like throw stats in there. What is going to have to be true about one of the angles and why? The key part is that one of these sides is a diameter. Okay? One of the parts of this inscribed triangle I'm going to make sure is a diameter. So what do I know about one of the angles? What's got to be true?
No, I mean like.
Oh, sorry.
Oh.
Oh boy. Okay, what do we talk about? What do we just look at on the front side? What do we find measures of? Not central angles. Inscribed angles. Okay. Let's find maybe an angle that we can combine with the stuff on the front side and get some measures. Now.
Okay, so what is that? We learned like on the front side that
Yep.
right, is gonna be 2 times the inner angle.
Okay, so
then the inner angle is gonna be half of the arc.
Okay.
So AC would be the arc, and then angle B, and since it's a straight line,
this is
I
R.
mean like the.
Yeah, continue. Keep
Okay,
on.
it's be 180 degrees because it's like a straight line. I mean, yeah. Yeah, that's right. Yeah. And then, so. And then, so, B would be 90 degrees, because like half
So then the angle that's opposite of this diameter must be half of a semicircle, which is what Val just said. Half of a semicircle, half of 180 is 90. So we'll always get a right angle if we have this setup. We'll always get ourselves a right triangle if we do this. So if you have an inscribed triangle, and one of the sides is the diameter of this circle, then what's always true is that then the triangle must be right. And even more specifically, the angle opposite of the diameter must be a right angle. Okay. The converse of this is also true, and I believe the book has a separate theorem for this. The converse is also true. So if I give you a triangle, an inscribed triangle, and it happens to be a right triangle, if I give you a triangle, I tell you it's a right triangle, and it's inscribed in a circle, then we definitely know that the hypotenuse of that triangle is got to be a diameter. It's got to go through the center of that circle. Okay. If you inscribe a right triangle, then the hypotenuse must be the diameter, or a diameter of that circle, is the converse. It is also true. In the book listed as a separate theorem. I just did. Let's talk about quadrilaterals real quick. Kind of a similar game. Let's now, instead of a triangle, let's inscribe a quadrilateral. So I'm going to just make up a quadrilateral in here. I'm putting 4 vertices on the edge of a circle. I'm going to inscribe a quadrilateral this time. For an inscribed quadrilateral, let's look at. I'll give you a little more direction this time. Let's look at a pair of opposite angles. What I mean by opposite angles that are across from each other, non-adjacent. So like A and C, and B and D would be opposite angles in this case. Did anyone see, or can anyone think of, like, maybe hypothesize what a relationship between, say, any pair of opposite angles in this inscribed quadrilateral should be? For example, how should A and C be related to each other, and how should B and D be related to each other? Think inscribed angles. Okay. Do they necessarily have to always be half of each other? I don't think they have to. You likely could position it such that it's true, but it doesn't have to. How about this? I'm going to take a second. I'm going to erase the labels for these two, so we're only focusing on, say, A and C. How would you calculate what angle A would be? How would you calculate what the measure of that angle should be? What could you do if you knew something about the arc, some arc measures going on in there? How would you go about calculating what angle A should be? What would you like to know? It's half of its included arc, right? So if you knew what, say, this arc was, you can just take half of it, and that would tell you what angle A is, right? And you could repeat that same process to find what angle C is. You just take this chunk, and if you found half of it, then you know what angle C is. What happens if you add those two arcs together? What's the measure of that arc that you would add together? 360 goes all the way around the circle, right? What do you know about the relationship between that inscribed angle and the arcs? How do those things relate to each other?
Oh. So then we just do 360 divided.
If I know that if I could tell you what this part is, half of it's A. If I knew what this part is, half of it's C. Okay? So what if so then if I added A and C together,
Then you would get.
if I took measure of angle A and I added it to the measure of angle C, then I would end up with, well, half of this, and let's see, there should be half of this arc and half of this arc. Well, if I add those things together, what degree measure do I end up getting? If I add half of this chunk plus half of this chunk, 180. I'm not saying that I'm not saying those angles are congruent to each other. But if I add these two angles and I get 180, or half of this arc measure of the whole circle, what do I call two angles that add up to 180?
No.
Supplementary.
Thank you, Ben. The inscribed quadrilateral theorem says just that. So then you can play that same game. If you erase these arcs on the outside, you can play that same game with, say, B and D. Because you still get you get a chunk of the circle and then the remaining chunk of the circle. The inscribed quadrilateral theorem says that opposite angles of an inscribed quadrilateral are supplementary. Again, it's this reasoning. If I look at just two pair of opposite angles, the outer arcs that they include must be 360. So when I add those things together, half of it is whatever the angle measures are. So these quadrilaterals, any pair of opposite angles in an inscribed quadrilateral must be supplementary. They must always add up to 360. I don't have examples from the first theorem, and I apologize for that, but you'll have some in your homework, which we'll get a chance to get started on pretty soon. I do have some for this inscribed quadrilateral idea. So, for example, in this, in our little case here, I have inscribed quadrilateral STUV. Notice it's inscribed because all four vertices are on the edge of the circle. I don't really know much about what any of these are individually. This just happens to be a trapezoid. Doesn't have to be a trapezoid, but it can work out to be a trapezoid. But I do know that from my previous theorem that any opposite pairs of angles must be supplementary. Or in this case, 2x plus 64 must be 180. Angle S plus angle U, in addition, these two are opposite angles of this inscribed quadrilateral. They must also be supplementary. Okay? And you can solve each of those two equations to come up with what the values of x and y are. In example B, I don't give you the same setup here. How can I find one of those two angles? Let me find, let's say, like angle, either x or y. Okay, what could we do? Courtney, what are you gonna try? And what angle will I find? X. Courtney's going to use the idea, since x is an inscribed angle, she's going to look at this ice cream cone, this the included arc, and just divide that measure in two. So she's going to take angle x, better be whatever, 52 plus 80, and divide that thing in two. 52 and 80 is 132. Half of 132 is what, 66? Was it?
It's just 66.
X has got to be 66 degrees. You may think to yourself, maybe I'll just try that same thing to find y. Unfortunately, there's nothing here that says what the measure of arc JN is. So we can't apply that same game to find y. What could you do to find y, though? Val? You could use, we certainly could use our previous theorem here, since this is an inscribed quadrilateral. Opposite angles better be supplementary, according to our previous theorem. So then whatever y is, plus 114, that better be 180 degrees from our previous theorem. So then y better be what, 66 as well? I don't know why I chose to inscribe why I picked diagrams that both have isosceles trapezoids in them, but I don't know. I did not mean to imply that inscribed quadrilaterals must be isosceles trapezoids.